Welcome to The Explainer. You know, they say the best time to plant a tree was 20 years ago, but what if we could change that math? Today, we're digging into a pretty fascinating scientific proposal that wants to do just that. It's not about just planting a tree, it's about putting it on hyperdrive. I mean, really think about that for a second. When we talk about restoring a forest, or even just adding more green to our cities, we're talking about a timeline of decades, right? That's a project for the next generation. But let's be honest, with the challenges we're facing, we kind of need solutions, well, yesterday. So the question becomes, can we find a fast forward button? Okay, so here's the headline number. We're not talking about a little boost, like 10 or 20% faster. The proposal we're looking at claims a potential 6 times increase in growth speed. Yeah, you heard that right, 600%. It sounds completely nuts, almost like science fiction, but stick with me because the science here is surprisingly detailed. All right, section 1, a 6 times faster forest. So the big question is, how on earth is something like that even possible? Well, it's not some magic bullet. It's a whole system, a complete rethink of how we grow a tree, right from the very start. The official name for it is the Accelerated Tree Growth System, or ATGS for short. And the key idea here is a massive shift in how we think about this. You know, normally we plant a sapling, cross our fingers, and hope for the best. ATGS throws it out the window. It reframes the whole thing as a continuous production process. The best way to think about it? It's basically a high-tech tree factory. So let's peek inside this tree factory. What's actually going on in there? Well, it's not like one single gadget. It's more of a whole philosophy, built on 3 main pillars that all have to work together. The goal? To create the absolute perfect 5-star resort for a tree to grow like crazy. Okay, so what are these 3 pillars? First up, you've got optimized light. We're talking about giving the tree the perfect diet of light, 24/7. No waiting for the sun, no cloudy days. Next, you have engineered biology. This is where it gets really cool. They essentially supercharge the soil by creating a custom-built team of microbial buddies to help the roots. And the third pillar is intelligent support. And this is crucial because if a tree grows that fast, it can get kind of floppy. So this is about physically propping it up so it doesn't just break. Okay, section 3, the growth recipe. So we have these 3 big ideas, right? Light, biology, and support. But how does that actually translate into a process? Well, it turns out it's a very specific step-by-step recipe designed to squeeze out every drop of potential growth. And this is pretty wild. The process actually starts before you even plant the seed. Step 1 is to prepare it with these special coatings. Think of it like giving it a little nutrient-packed jacket. Then step 2 is all about the roots. They're inoculated with something the paper calls a biocassette, which is a fantastic name. It's basically a care package of helpful microbes delivered right where they're needed. And only after that foundation is laid do you get to optimizing the light and installing these special sleeves to support the stem. This chart really puts it into perspective, doesn't it? On the left, you have standard planting. You know, passive sunlight, whatever microbes are in the soil, it's a game of chance. On the right, you have the ATGS method. Everything is actively managed. Instead of passive sunlight, you have managed light. Instead of just native microbes, you've got an engineered dream team. It's the difference between hoping for growth and, well, engineering it. All right, section 4, the math behind the magic. This is where you might be thinking, okay, this all sounds cool, but a 6 times gain? How do you get to that number? This is where the whole thing gets really clever, because it's not just about throwing a bunch of tech at a plant and hoping for the best. It's all measured. The secret sauce here is something called KPI gates. KPI just stands for Key Performance Indicator. You can think of these as checkpoints or levels in a video game. You can't move to the next level of enhancement until you've proven you've passed the current one. So, for instance, the system might have a goal for the microbes to produce a certain amount of nutrients. It uses sensors to check. Only when that goal is met, when that gate is passed, does it unlock the next step, like adjusting the light. It's a feedback loop. And this is where that big number comes from. Each of these gated improvements doesn't just add to the total, it multiplies it. It's the power of compounding interest, but for biology. So you get a 2.2x boost from better light. Then you multiply that by the 1.15x from tweaking the light schedule. Then multiply that by the 1.3x from the microbe team. You see how it works? You layer all these conservative estimates on top of each other, and suddenly you're looking at a total potential gain of almost 6 times. But, and this is a really important but, the paper is super clear on this point. This is not a guarantee. That 6 times figure is what you get if everything works perfectly. It's the absolute best case scenario, and it's completely dependent on every single one of those KPI gates being passed successfully. If one step fails, the whole compounding chain is affected. Okay, so let's move on to the big picture. Section 5, from blueprint to biosphere. Let's assume this works, even if we only get, say, a 3 or 4 times gain. What could we actually do with this technology? The possibilities are, well, they're huge. For one thing, you could use it for major ecological repair jobs. Imagine land that's been damaged by salt, making it hard for anything to grow. You could combine this system with trees and microbes that are naturally salt tolerant and potentially bring those areas back to life way faster than nature ever could on its own. The paper even points to places like the Mesopotamian basins as a possibility. Or what about our cities, our concrete jungles? You could set up these ATGS nurseries as hubs to rapidly grow trees specifically for urban planting. You could create green buffer zones around cities much, much faster. The paper even suggests you could add other cool features, like things to help reduce air pollution, or even protect birds from flying into buildings. Here's another great one, protecting riverbanks. Erosion is a huge problem. With this, you could strategically plant fast-growing, deep-rooted vegetation along rivers to lock that soil in place. It's about using this speed to stabilize sensitive areas before they wash away. Okay, deep breath. We have to do a reality check here. As cool as all this sounds, the paper's really honest about the challenges. For starters, when you grow things that fast, they can be weaker, more brittle. Then there's the energy cost. Running all those LEDs and sensors 24/7 takes a lot of juice. And you have to be incredibly careful when you're introducing engineered microbes into a new environment. And maybe biggest of all, this is still a blueprint. It needs a ton more testing on different trees, in different places. And maybe this is the most crucial point to understand. The people behind this aren't trying to sell you a product. They're very clear that this is an open design space. It's a blueprint, a set of ideas, and a framework that they want other people to take, to test, to break, and to make better. This isn't a for-profit gadget. It's an open invitation to the scientific community to come and play. So where does that leave us? Look, it's a bold idea. It's complicated, and there are some really big hurdles to clear. But it forces us to ask a really interesting question. To what extent can we, and maybe even should we, use our technology to accelerate nature's own healing processes? It's a huge thought, but it's one worth thinking about. Thanks for joining me for this explainer.